Okay, so I'll be talking about a completely different system, but also here at Wright Lab, to use little levitated, this is a 100 nanometer silica glass particle levitated in a laser floating in the center of the vacuum chamber. So we can trap actually 100 nanometer up to several micron size dielectric, just glass particles for the purpose of a laser, just by focusing that laser. So depending on the size range, we can go from femtogram masses, it's 10 to the minus 15 gram masses up to tens of nanograms, more than 6 orders of magnitude heavier, with a couple of different variations of how we focus the laser. But these are traps we have here over on the other side of Wright Lab with these small particles and larger particles. And maybe the exciting thing about this is we're also starting, especially on the small particle side, to reach real constraints from quantum mechanics on how well we can measure the position of these particles and infer tiny forces acting on them. So as Conrad said, maybe we have this beautiful little sphere floating there in the center, and we want to get a little kick. The equivalent of us punching the hole in the cavity is, shining laser photons on it to see where it is. There's always some measurement you have to do, and that measurement's going to impact the particle and affect the back action. The way we change the state of the particle from those photons hitting it is, when we balance that, is hitting the standard quantum limit for us. So everybody has different standard quantum limits, but this one's ours. Recently, maybe we're starting to show we can reach actually sufficient force sensitivity to be able to see forces imparted by single subatomic particles, the types of things we're interested in nuclear and particle physics. In nice work from Joe Schoen, our student, we recently detected alpha decays where you put a radioactive nucleus inside these little glass particles. An alpha particle shoots out, the nucleus recoils, and actually as it stops and rattles around in there, by momentum conservation has to push on the sphere and the entire sphere recoils. So we can see these really tiny forces. In SI units, that's 10 to the minus 21 Newton seconds, but maybe in more conventional particle physics units, we can reach like MeV sort of momentum sensitivities. What we're really excited about is now going and doing neutrino physics, where we can put radioactive nuclei that emit neutrinos coming out of the spheres. You'd have no hope of detecting a neutrino that comes out of a nuclear decay. It would go through a light year or more of lead without interacting. But event by event, we can see the nucleus recoil as it leaves, and we can sense invisible particles coming out of our spheres. And maybe just to say, since this is the quantum session, you can really think of these little spheres floating there in space as a quantum harmonic oscillator, and we're able to measure their position and momentum quadratures of their motion with uncertainty approaching the kind of 0-point motion of the particles in the trap. So if you hit it one time, so we're looking for it to get a little kick in P, a little kick in its momentum, a force interacting on the particle as these invisible particles that we otherwise couldn't see with sensitivity here, essentially the 0-point motion. So I think, LIGO, of course, has improved fundamental physics measurements by squeezing. We also heard from Conrad and the Alpha and Haystack teams about improving fundamental physics with squeezing. I'm not aware of basically other demonstrations to date, but the hope is that we're getting now to the 0-point or kind of standard quantum limit, and then hopefully we can also squeeze and go beyond as has been demonstrated in these experiments. And just to say, we want to make a big array of these particles, surround them with particle detectors. And for the experts, this is a plot of the parameter space looking for heavy neutrinos. There might be heavy right-handed neutrinos we haven't seen before. And over some wide range of masses, these are kind of the existing sensitivities where we can see 1 in 10 to the 3 decays going to these heavy states, and maybe we could reach as low as like 7 or these matching lower branching ratios to these decays. Okay, so if I have just 30 seconds later, I can say one more thing. Okay. So that's all on neutrino physics on a tabletop. Super fun for some of us who work on big neutrino experiments, which have huge detectors and mines and things like that, to be able to ask interesting questions about neutrinos on a tabletop. Another thing we're thinking about in our lab, and this is really new work just getting started, is whether we can measure gravitational interactions between these quantum systems, and particularly like what's the gravitational field from a massive particle, one of these little nano microparticles in 2 places at once, or in a superposition where its spatial wave function is delocalized. It's a question you can ask in principle. It's always been a thought experiment, but the community is just starting to try to think of experimental realizations. And we've started, here using a spin and a nanodiamond, for instance. We've started some work. This is a nice picture from Aaron, our postdoc, showing the trapping of 2, in this case, graphite particles, which we want to switch to diamonds and then see if we can measure, to start with, interactions other than gravity between them, because we have to get rid of all the stray electric charge and things that could prevent us from seeing the gravitational interactions. So that's also getting started here at Wright Lab. If you're interested, we're happy to show you the labs. Thanks.